Good day. My name is Abdulrahman Al Qawasmi. I'm from the Far University, from Electrical and Computer Engineering Department. In this presentation, I will summarize our accepted paper on the hybrid energy, IoT feedback irrigation, and ultrasonic tank monitoring system for greenhouse agriculture. The key idea is to make irrigation decisions from crop profiles and sensor feedback, protect the water tank and pumping, and connect water saving with hybrid PV diesel energy economics. The motivation starts from a very practical farm problem. In greenhouse agriculture, fixed irrigation schedules are simple, but they do not see the crop, the soil, moisture, the tank level, or the energy cost. A pump may run when the tank is too low. A hidden leak may remain unnoticed, and different crops may receive the same irrigation even though may require different moisture and root depth settings. Therefore, our design treats irrigation, tank protection, IoT monitoring, and energy supply as one integrated problem. The research gap is an integration gap. Existing systems usually address soil moisture as cloud monitoring or energy supply separately. Our contribution is to combine crop profile irrigation, root zone water estimation, ultrasonic tank level safety, remote alarms, and hybrid PV diesel pump economics. We also clearly separate the validation layers so that the bench ultrasonic result, the 24-hour simulation, and the energy economic model are not presented as one physical experiment. Here is the proposed architecture. The sensing layer measures temperatures, relative humidity, root zone moisture, and ultrasonic tank level. The ASP32 Edge controller filters readings, supplies the selected crop profile, and generates pump commands. The activation layer drives the pump or valve through relay or contactor control. The cloud dashboard supports remote monitoring, notification, and manual override. Finally, the pump is linked to a PV diesel hybrid supply so that water-saving operation also has an energy-saving impact. The control cycle is intentionally simple and explainable. The farmer selects a crop profile, for example, tomato or cucumber. The node needs temperature, humidity, soil moisture, and tank level. It checks whether the greenhouse is within the crop-specific limits, computes the irrigation pulse, and then sends pump or valve commands only when the soil moisture and tank condition allow safe irrigation. The same cycle updates the IoT dashboard and sends alarm when conditions are abnormal. A key feature is the plant profile. Instead of one irrigation threshold for every crop, the system uses initial settings for crop temperature, humidity, soil moisture, and effective root depth. Tomato, cucumber, lettuce, and mint or basil can therefore receive different irrigation behavior. These values are engineering starting points. They must be calibrated locally according to cultivar, greenhouse ventilation, salinity, sensor depth, irrigation method, and growth stage. For the tank branch, the ultrasonic sensor estimates the air gap from the sensor to the water surface, then converts it to a tank level percentage. In the capstone verification matrix, the subsystem achieved 1.42% mean absolute error, which is sufficient for threshold-based dry run protection and leak alarms. However, it is important to interpret this correctly. It is a controlled distance verification result, not long-term validation in a physical greenhouse tank. In the 24-hour tomato-like greenhouse scenario, the fixed schedule used 120 minutes per day of irrigation. The feedback controller operated the pump for 78 minutes per day, maintained soil moisture inside the selected profile band, and reduced water application and runtime by 35%. Additional cucumber-like and hot-dry disturbance cases gave reductions around 29%. These results show the controller's responsiveness, but they remain initial simulation results that require future field validation. The energy layer uses present worth analysis. In the reference farm scale model, the PV diesel alternative reduced present cost from 384,923 cost units to 229,570 cost units at a 10-year life and 10% interest rate. This gives a 40.4% present worth cost saving. To avoid overclaiming, we also explained that the 30 kilowatt diesel and 13.4 kilowatt PV values are a reference energy layer, while greenhouse demand must be recalculated from the actual pump rating and the simulated pump runtime, such as 78 minutes per day. Tank level slope provides a second safety signal. During normal irrigation, the observed tank level decrease should be close to the expected decrease. If the observed loss is too large, the system can raise a leak or pipe fault notification. If the tank level is below the safe threshold, the pump command is forced off even if the soil is dry. If the cloud connection is lost, local control continues and synchronizes later. When presenting publicly, it is important to separate what is supported now from what still needs future validation. The paper supports an ultrasonic verification error of 1.42%, a 35% reduction in a simulated 24-hour irrigation case, and a 40.4% present cost saving in the reference PV diesel economic model. It doesn't claim long-term physical greenhouse field validation yet. Future work should include deployment, flow meter measurements, moisture depth calibration, cybersecurity assessment, and a more detailed hybrid energy dispatch model. To conclude, the proposed system integrates crop profile feedback irrigation, ultrasonic tank monitoring, leak and dry run protection, IoT dashboard functions, and hybrid PV diesel pump economics. The main take-home message is that smart greenhouse irrigation should not only switch a pump based on a soil moisture, it should protect the crop, protect the water source, and reduce the energy cost together. Thank you for watching this presentation.